Is the following statement true? That for all integers a, b, and c, if a divides b and a divides c, then a divides b times c, or the product of b and c. Well, let's think of some examples, right? The examples we've been looking at so far are things like if a is 2 and b is 4 and a is 2 and b is 6, then is it true that 2 divides 4 times 6? These are not great markers. Gosh, okay. Let's use this one to rewrite this a little nicer. 2 times 4 times 6, 2 divides 4 times 6, which is 2 divides 24, and of course that's true because this can be written as, 24 can be written as 2 multiplied by some integer, in this case 2 times 12, right? Let's think of 3. 3 divides, let's do 9, and 3 divides, maybe let's not do 15, let's do 3, 6. So does 3 divide 9 times 6? I realize that this divisibility sign oftentimes looks like a 31 or a 21. It looks like a 1. Keep in mind it's not a 1. Maybe I'll write it a little bigger so it's a lot more obvious. Yeah, I think that'll be a lot nicer. Anyways, this is the same as saying 3 divides 54. And that's obviously true because 54 can be written as 3 multiplied by some integer. In this case, it would be 3 multiplied by, I think it's 16. No, it's not 16. 18, I think. 18 times 2 is 36. 36 plus 10 is 46. 46 plus 8 is 54. Yeah. Okay. So, and of course, all of these share the relationship that this is all, both of these is the same as saying 3 divides 3 times 12? Oh, sorry, 2 divides 2 times 12, and this is the same as saying 2 divides, or gosh, I'm getting these mixed up, 3 divides 3 times 18. Really? That's all we're asking. So we're going to be looking for the fact that what's on the left is something on the right times an integer. Okay, so this is looking like it's true with our examples. Let's give it a shot and try and prove this. So how do we start? Well, this is a let proof, right? This is a for all proof. Oh, actually, no, let's quickly just rerun our definitions again. I know it gets tedious, but it's important to be always reminded of what we mean by a divides b. Just basically saying a, b, and I'll say k are integers such that b can be written as a multiple of a, or b can be written as a times k. Fantastic. That's how we're defining divisibility. You can, of course, just replace this with the word divisibility. Okay, now we can actually start writing our proof. How do we start? This is a for all proof, so we start with let a, b, c be integers such that a divides b and a divides c. Then, what do we mean by a divides b and a divides c? Then we can just say, this is the same as saying b can be written as a times m, or b can be written as a multiple of a, where, or actually, yeah, let's write this a little bit different than I have so far. B can be written as a times m, and c can be written as a times n, where m and n are integers. Fantastic. Defined everything, supposed everything we needed to. We can now start verifying our Q statement. So let's start with just the right-hand side. Let's say next, b times c is the same as saying am multiplied by an, which is going to be the same as saying a squared multiplied by mn, okay, which is really just the same thing as saying a multiplied by amn, where we should recognize, actually I guess we don't really need to say this, we can just immediately jump here, but we can just say where a, m, n are in fact integers, so a divides a, open bracket, a maybe you could argue that a divides a squared mn. I'm going to assume you would need to prove that too. So we're just going to stick with our well-known assumption that you can always go from this to this. A divides B times C. Okay. Or maybe we can say A divides AM and then AN. So, and then we can write an arrow. A divides BC. Okay. This is super duper explicit. I decided to split this into A times something. You can probably keep the A squared and then argue that A divides A squared MN, so A divides B times C. My only worrisome is if your teacher is really strict or something, they might ask you to prove that A divides A squared, although that's a very trivial proof. Or maybe it's even tautological, but there we go. We've now proven that this statement is in fact true for all A, B, and C that are integers.